Hello. I don't know where to begin, but this video is basically an introduction to me attempting to make some progress on Bohmian mechanics related physics things. I'm going to be not very articulate because I'm not used to making videos like this. But I'm just gonna blurt out a bunch of stuff, and look, if nobody watches this, it's not necessarily for that, it's just for me to have something to speak to as I attempt to make progress. So what's the situation? I'm free here in Leipzig. I'm working, I would say, very much just part-time. And I kind of figured that while I'm in Germany, it would be a shame, to not finish this physics stuff because I have ideas that I truly do believe in when it comes to some very abstract stuff. Although in that the word abstract is very relative because it gets way more abstract than this, but but when it comes to the way that measurements are predicted in quantum mechanics outside of position measurements. And I really believe that there's some kind of treasure of truth in this. And it's a great direction to attempt to make progress in quantum mechanics. And for that reason, even though I feel honestly awful about physics sometimes, it would make me proud at least to publish my ideas, to attempt to do a good job of investigating what I'm thinking and make steps towards that and eventually have something that I feel is a congruent work. That I feel is I don't mean congruent, whatever. Publish something that to me is a good explanation of what I've done. I was just reading, okay, let me introduce a little bit of what I have. And I guess I'm gonna get a little bit physicsy when I talk about this stuff. And I guess I'm not gonna be worried about releasing this stuff into the public because, random people's ideas about quantum mechanics are, wouldn't even say a dime a dozen. You have to pay people to even give a shit about them. So I don't think that's too big of a concern. And in the end, whatever. So let's take a look at something like a paper that I wrote as part of my master's thesis. And that's kind of the core that I built, hoping that future Felix was going to follow up on it and actually do something. And while I do want to spend time working on my, I want to say career, or really as I see it, just ability to finance my own life, potentially future life of children and things like that. I guess I don't feel that it's necessary to invest myself 100% in that. / I don't want to, because my heart's not in it completely. So I've had troubles with physics before. It's a hard subject, and the people are also hard a lot of the time. But I'm gonna try to, I'm not feeling great about it. There are ups and downs, but I'm gonna try to make a little bit of progress every day that I work on this, which maybe 2 days a week, something, and we'll go from there. I may not be able to accomplish anything with this, but I know that there's a lot of potential in it. Which is difficult. Let's begin. So here we are. Momentum in quantum mechanics. Don't remember which version means what, but here is the gist of what I want to accomplish. I'm gonna make this a bit bigger. I don't think it's legible on YouTube, but you know what? That's fine. And it seems to mostly cover everything, so. I'm not gonna go through everything here. I'm just gonna verbally kind of try to explain it. Basically, it all comes from the noticing that momentum measurements at the Large Hadron Collider are actually done through position. And this is a simplification, I think, of what's really going on, but supposing you have a particle moving in a circle, you infer the momentum of that particle by the classical formula relating its radius of that circle to the momentum if you know the charge and the strength of the uniform magnetic field that it's in. So then the question becomes, what are you really measuring here? Because if the instruments that you're working with only really convey position information, and then you use that to infer a momentum, why would the particle be in a momentum eigenstate after your measurements and not a position eigenstate after your measurements? Now that is a naive question already because it assumes the whole measurement formalism of quantum mechanics, which, you know, people who I think subtly enough about it or precisely enough about it know that it's already kind of just a intermediate guess and not really to be taken seriously. But nonetheless, what this means, the fact that that the momentum of a particle is inferred by means of doing a number of position measurements means that if you were able to predict the probabilities of those outcomes of position measurements, then you could infer the probability distribution of momenta. So if, let's say that, and this is, normally I think there are far more than this, but let's say that 4 position measurements are done to determine the radius of the circle, and we fit those 4 position measurements to the best possible circle, given the uncertainties of the measurements and so on. If you have the probability distribution of the outcomes of those 4 position measurements, then you can directly use that pretty simply to derive the probability distribution of corresponding momentum outcomes that we would infer. And the question is, does that agree with the Fourier transform, which is the traditional way used to measure momentum or to predict the probabilities of momentum measurements? And the answer is no, it doesn't, because the Fourier transform is just one well, I'm not going to say it. But I looked into this question for a simpler case, and basically the answer was that depending on how spaced out your position measurements are, how far the particle flies in the time between when you want to first measure the momentum and when your final position measurement occurs. The agreement with the Fourier transform varies, and there's a limiting case where the particles do limit the predictions do limit to the Fourier transform, but the agreement is, I want to say, never 100%. It's just a limiting case. And that would mean that any predictions that come from direct momentum space predictions in quantum mechanics are only an approximation, assuming the position measurements are correct, which we have no reason to believe otherwise, especially because the detectors are actually measuring position directly. Now, the problem with that is that quantum field theory, you kind of lose position space and you make your predictions through momentum space directly. You start just with momentum eigenstates. Nobody does, well, at least in the canonical quantum field theory thing is just predictions in momentum space. And so all quantum field theory results would be affected by momentum space results being unreliable. So that's the situation. And I mean, I think it's in some ways amazing. You know, I mean, it would, I mean, I think it, I don't even want to say it would show that quantum field theory is not fundamental. I would even go as far to say that it's a strong argument that quantum field theory is not fundamental, although we sort of already know that because of gravity and whatever. And when I say quantum field theory, I mean the standard model. But even outside of gravity, the predictions of quantum field theory, obviously, if this is true, which I think it's a very strong argument, then the predictions of the standard model are not fundamental even outside of the presence of gravity or a few of the other like known problems in quantum field theory. So I'm kind of battling with myself, to be honest. I guess this is also kind of just a journal for me, a way for me to express how I feel about doing this. And so it's kind of weird to post on the internet, but it's nice for me to have something to talk to and talk through this thing. So that's basically the general thing that I want to do. Now, I feel kind of sad about, where I stand now, but, I'm going to release this shitty video and then we'll see what happens. So, turning that into what comes next, into actual steps of things that I can do, I made myself a little bit of a list. The first thing is all of this rests on the assumption that momentum measurements do in fact occur indirectly through measurements in position space. Basically measurements, well, I could go more into that, but the question is basically the, potential for corrections to momentum space to exist depends on whether you can make predictions for momentum experiments using only predictions for where the probabilities of where the particle will arrive, so position, when the particle will arrive, so arrival time, and then also the particle number and type. And I want to say that I don't think I'm forgetting anything here, but maybe there's something else that we could potentially incorporate. But the question is, I mean, obviously for this simple Atlas detector, they also do it at CMS. It's a generally used particle detector technique to infer the momentum from the radius. Obviously, in this case, you need the position information to infer the momentum. So in this case, it is in fact true that you can find corrections to the Fourier transform. However, to validate that for momentum experiments in general, I basically have to do a literature review and look at all this stuff that has been published about all kinds of mechanisms and devices that were used to predict momentum, or to measure momentum in practice. So I already have downloaded a bunch of different sources. The best one so far, at least one very good one so far, is from the Particle Data Group review, which is like a 2,000-page thing, but they have chapters that are specifically on devices that are used to measure properties of particles. So just review a bunch of experiments and check that, yes, in fact, at least in principle, if not in practice, there could be and would be corrections to the Fourier transform as a result of measuring in position space, and that there is no such thing as a direct momentum measurement, which is kind of an idealization that theorists, use not to really think about the dirty details of devices and measurement and stuff like that, which makes the theory less clean. Okay, so that's point number one. Why don't I number these? Because that is just nicer for my brain. Number two, get good at Bohmian mechanics part one. So contingent on some of this stuff, Bohmian mechanics is actually quite, I would say, fundamental to this whole idea, because Bohmian mechanics makes the claim that you can measure everything through position, and therefore it doesn't have to make any direct predictions for momentum, because all momentums are position measurements anyway. However, when I talk to Bohmian people, like people researching Bohmian mechanics and whatever, they often try to justify this by saying, hey, look, at the end of the day, there's a pointer, like you somehow or another read the measurement off of a device, and the position of that pointer could be predicted using Bohmian mechanics if you complete the simple task of solving the Schrödinger equation for something times 10 to the 23 particles. So I think that, okay, sure, in principle, I guess, I think that's in some ways a valid argument, but I'm not talking about that. I'm talking about, predicting the motion of a particle, a single particle that's moving somewhat circularly, in order to make corrections to the Fourier transform. And that's actually something that a priori seems doable. Now, whether it's extremely easy or extremely difficult but doable, or just not doable and needs computation or something like that, I don't know, but it's at least at the level, the order of magnitude where, it could very well be doable. And apparently, according to Sidon, we have exact solutions for, I think, Gaussian particles moving in a constant magnetic field. So that sounds very promising. Okay, so Bohmian mechanics, that was just an introduction there. Why is it relevant? Well, I have so much to say here, but yes, I've kind of already said a little bit that it relies on the same premise, I would say. But in addition to that, some of these predictions, for example, any prediction involving arrival time, or even involving position measurements that aren't done at a fixed time, but are done at a, kind of like a double slit experiment or a screen where the particle can just arrive whenever it wants to, and you're not choosing a time to look for it. Regular quantum mechanics has problems with that, which is kind of hilarious because like everybody talks about how quantum mechanics is, there are no issues and you're a fool if you're trying to find issues with it and you just want things to be classical again. And yet, even in simple, it's not that hard to devise experimental setups where there are problems. Now, if you're a traditionalist watching this video, this is probably, if you didn't already think that I was a fool, you're gonna think so now. But, I'm saying things that seem stupid, but I'm sure that you haven't looked very carefully at them. So, scientifically, you can't say that I'm wrong unless you have. And I have. So, yeah, these are actually legitimate issues with quantum mechanics that, well, they're not in the mainstream, I guess. Which is actually fascinating because I think they're super important and yet unpopular, which is such an opportunity. Anyway, yes, I do want to get better at Bohmian mechanics. Number 2 says, let's understand the measurement problem in Bohmian mechanics better, because I have made assertions in the past, including to Sabine Hossenfelder, who kind of is one of my goals is to, prepare something good with her and establish some kind of communication with her, because, well, she's the symbol of skepticism among physics, although I'm sure that there are hundreds of other physicists who have thought the same way. So, whatever. And in the end, I don't need that, but I also just like her. We did have a conversation once about Bohmian mechanics, and I found her to be extremely rational, which I really liked, and I totally vibed with that. So I guess she's kind of an idol for me, to be honest. Anyway, although we had a weird interaction where I didn't want to get credit for the information I gave her on Bohmian mechanics because her video didn't end up matching my understanding of the theory. And yes, of course, I don't always agree with her. However, she's kind of a hero in some ways. So, I don't know. At least that's how I feel at the moment. Ask me tomorrow, who knows. But anyway, yes, I do feel that I've understood, relatively well the measurement problem. However, everything is subtle, especially when it comes to measurement in quantum mechanics. There's insane subtleties, and things that are obvious and you feel like a fool for even thinking about them end up not being true. For example, the equivalence of Bohmian mechanics with quantum mechanics, which the first time I doubted it, I spoke to another bachelor student in the class, and I was a master's student at the time, and I was like, I really wonder if it's completely true. I mean, it seems right. And she's like, I mean, it's just obvious, isn't it? I mean, and I was like, yeah, it's obvious. But I was like, no, it's not obvious. And I felt stupid at the time. But at the same time, my emotional brain felt stupid, but my logical brain was like, no. The simple fact that, fixed time position measurements are the same doesn't mean that the theories are completely equivalent, because you can measure all kinds of different things. And who knows about all those other things? I don't know why people jump to conclusions sometimes. They don't want to think as much. It's complicated as fuck to think all that, whatever. Let's finish this video. So, number 2 was get good at Bohmian mechanics by understanding the measurement problem, and I do want to release a video about that at some point. And I might kind of, do whatever I feel like among these points, because honestly, today I had some problems with motivation, trying to look at all these experiments that were done, it was a bit brutal. So that's part of why I'm making this video, because I'm trying to motivate myself. And I may, the idea of releasing a video on the measurement problem of Bohmian mechanics, I think that's going to be very satisfying. So I may work on that, kind of in tandem with number one, because I want to, play to my motivations. All right. Wow. If you have watched this video up to this time, and it's like, within the next 3 months, then I will Venmo you $20, at least the first person. So get in touch with me if you've actually watched this, because that would be freaking hilarious. If you see this, just send me an email at, what email do I give? Well, I think it's felixphysicschannel@gmail.com. Yeah, it is. Send me an email there, and I'll Venmo you $20, just because I don't think any person living will ever watch this. Maybe in the far future, I don't know. Anyway, get good at Bohmian mechanics part 2. Figure out the situation with relativistic Bohmian mechanics. I don't know if it's a thing, to be honest. I had good third-party information that basically Bohmian mechanics did not have a working way to make the predictions that the standard model does. However, that's what I told Sabine Hossenfelder as well. And then she included that in her video. And then we got a bunch of Bohmian guys in there like, your video was great, but you're wrong. So, like, I like you, but you're wrong. And they were very upset. And I was terrified of having been a source of misinformation. I originally heard that from many sources that there is no working standard model for Bohmian mechanics, including from a PhD student of one of the authors of the paper that got referenced on that Facebook response to Sabina's video. The author of the paper that supposedly solves QFT in Bohmian mechanics, his student told me that there is no relativistic Bohmian mechanics that for the standard model. And also all of the researchers of Bohmian mechanics in my Bohmian mechanics group in Munich likewise told me that there is no working standard model in Bohmian mechanics. Siddhant told me that as well. I mean, sure, he didn't publish it, but he told me informally it's not working. Now, the thing is, Siddhant actually doesn't research that. He's just very in touch with all the Bohmian people, and he knows more than I do about Bohmian mechanics. So going from those two reliable sources and from talks that I had also heard in the past where they said in the talk that there is no relativistic working Bohmian mechanics and they're trying and whatever. I mean, okay, hold on. I should qualify that. Relativistic, yes, but standard model, no. Yeah, so I had a number of reliable third-party sources telling me that. However, I myself am not an expert in relativistic Bohmian mechanics, so I think that I told that to Sabina in our call, but honestly, I don't remember anymore. I think I did tell her that when it comes to relativistic Bohmian mechanics, I'm not an expert, but then again, hearing it from the experts myself, or people who should be experts, I found it reasonable to believe. Nonetheless, I would like to actually understand what the deal is with relativistic Bohmian mechanics, because that's the major complaint that everybody has with Bohmian mechanics. I'm losing my hair. Fuck. Anyway, whatever. that's the major complaint that people have. And I like Bohmian mechanics, and I do tell people that it has great things to offer, and I would like to have a sophisticated understanding of its flaws, in order to inform my opinion of how much I support the theory myself, because I think that there are amazing things about it to be learned, even if the theory itself doesn't end up being kept. I think it provides insights that regular quantum mechanics does not. In fact, I know that it provides insights, or at the very, very least, it provides insights on directions that you can make progress. And it provides a way to find issues with quantum mechanics. Anyway, so yeah, I would like to understand that better, and I want to get in touch with the very people who disagreed with me when I was speaking to Sabine, and be like, hey, I don't know my stuff, and I want to know my stuff. Can you help me? Like, can I come to your city and we talk about it a bit, and I will pay you for your time? I would love that, because direct contact with people is a very motivating thing for me, and I'm trying to work with motivation now. Okay, this is now a very long video, but we're finally at the last point. And I'm not going to start with this one for one reason or another. I just have to start with something. Number 4 is do an analysis of some measurement, for example, of momentum in Bohmian mechanics, and show corrections to the Fourier transform. I said Bohmian mechanics, but doesn't necessarily have to be done with Bohmian mechanics, but I have to actually do a calculation where I derive corrections to the Fourier transform. That's it. And I think it's October now, October, November, December. So I guess the next 3 months, I would like to spend a lot of time on this, because I'm in Germany now, and a lot of these people that I need to contact or that I would be working with or around are in Germany. All right. All right. It's been good. That's basically the end of this video. I may make one more video just on motivation, so that might come next.